Hello and welcome back. Today I want to continue talking about crystal oscillator related measurements by looking at how startup time is measured and what is its significance. Now, this is not a very complicated measurement, but it does require some specialized tools. So the other thing I will be talking about today is how a low capacitance, high impedance active probe can be built on a budget. So if you're curious, then keep watching. Until now, all of the measurements we looked at were concerned with how the oscillator behaves at steady state. But the startup measurement, like the name suggests, looks at the critical point when power is first applied and the oscillator starts oscillating. Basically, what we're interested in is the time it takes for the oscillator to stabilize and get to steady state, starting from when the power is applied. So the measurement is concerned with measuring this particular time period. Now, the delay time can be important if the system startup is critical. So if a microcontroller-based circuit needs to operate quickly after power on, you want the startup time to be quite short. But on the other hand, long startup time can also be indicative of some other hidden issues, like a low oscillation margin. Now, this measurement is carried out by directly probing the oscillator output pin before any series resistors, if any, are present. And this is where the problem starts. So as we discussed in previous videos on the crystal oscillator, this circuit is extremely sensitive to added extra capacitance. So most literature sources will agree that the probe that you're using to probe the oscillator needs to have 2 picofarads or less of capacitance, so that you don't affect the oscillator functionality and, well, the measurement outcome. And getting this sort of extremely low capacitance isn't really possible with passive probes. So not even the really expensive ones will be able to achieve such a low capacitance of below 2 picofarads. In most cases, what you will need is an active probe, since those are the only ones that can go so low in input capacitance. Now, the waveform that we will be observing, if we're using a proper probe, so something that can cover both DC and high frequency AC, will look something like this. So our first event is when power gets applied to the oscillator, and we should be probing a voltage increase up until the half supply point, and from there the oscillation slowly starts to build up, so oscillation rises slowly until it reaches a steady state. So the startup measurement that we're interested in is the time it takes from the application of the supply until 95% of steady state is reached. But it's important to notice that we can also perform this measurement using an AC only probe. So the oscillation part will be clearly visible since that is AC, but we should also be able to observe our startup event in the form of a spike corresponding to when the supply is first applied. So we can perform the exact same measurement both with a proper probe and with a probe that only has AC coupling. In both cases, we should be able to measure the time it takes between application of the supply and when steady state is reached by the oscillator. So how do we make a wideband ultra-low capacitance probe without breaking the budget? Well, you will find quite a few basic designs circulating out there, but the one that caught my eye was this thing. Now, this is the most simple circuit that I could find from a components count point of view, and there's quite a lot of documentation on it. So you have this instructables post on it, so just Google DIY 1 GHz probe and you'll find it. So here they go into quite a lot of details over the measurements, how it works, and so on. Apparently you can get this ready-made, so it's not that expensive. But the most interesting thing is this article. So this comes from the Electur magazine from 2004, and this is the oldest reference for the circuit that I could find. So here they give you the schematic diagram of it, some tips about how to build it, some measurement results, so how this compares to a commercial probe, and, well, some recommendations over how to measure it, how to build it, and so on. So the probe that I will be using today will be based on this design. Now, the only more exotic component that you will need to build this thing is this BF998 transistor. So this is a dual channel MOSFET transistor, also called a tetrode, that can be used in circuits up to 1 GHz. It's not a very expensive component, so if you can find it, it's just about 50 cents. So this will be the basis of today's circuit. Now, before building anything, I tried to first simulate the circuit. So what I have here is first of all an AC simulation. So for the main component for the transistor, I used the model I found online. So this is available on the NXP website. The only mention being that for some of the components, the values were defined as, for example, for inductors, L equals 0.12 nanohenry. So LTSpice didn't really agree to this and it was causing some errors, so I just deleted that bit. But anyway, coming back to the circuit, so we have our transistor, it's coupled through two 1 picofarad capacitors to an input sine wave, so this is used to keep the input capacitance as small as possible. Then we have a couple 2.2 megaohm resistors connected to ground. I'm using 2.2 megaohms because that's the largest resistor I have. Then from the source we have a 220 ohm resistor to the circuit's ground. The circuit is supplied from 9 volts. We have a resistor divider setting the ground point, so a 3.3 kilo ohm and a 4.7 kilo ohm. And then the output signal goes through 1 microfarad capacitor through some transmission line into a 50 ohm termination, so this will be in the oscilloscope or a spectrum analyzer or whatever you're connecting it to. So if we run the simulation and we look at what we get at the output, so I'm running from 10 kilohertz up to 3 gigahertz. Now the probe is supposed to work up until 1.5 gigahertz. But what we can see is that after a few hundred megahertz, the gain just shoots up. We'll come back to this a bit later. On the other hand, at the beginning, we have this high-pass filter effect. So below 100 kilohertz, the signal starts to drop off. And this is mainly because of the input low-pass filter constructed with the input capacitor and the input resistors. So in the AC simulation at least, the circuit seems to work just well. Secondly, I prepared the same circuit but with a transient simulation. So if we run this thing and we look at the output, so right now I'm inputting a plus minus 10 volt 1 megahertz sine wave, and we can see on the output that the signal is clipping on the bottom end, and there's all sorts of these artifacts going on, so this is some sort of simulation error. Other times I got it to completely oscillate, so that again wasn't really a very realistic behavior, but who knows. But if we set a more realistic, so 5 volt amplitude signal, so 10 volts peak to peak, we can see that our output signal is about plus minus 700 millivolts with an input of about plus minus 5. So the probe is attenuating the input signal by a factor of almost 10. And as explained in the article previously shown, you can fine-tune this by working on these capacitors. But anyway, the probe should work. It should work pretty well up until some high frequencies. And well, this is what I plan to use today to measure the quartz oscillator. So this is the board that I want to prepare. It's quite small, so 40 by 20 millimeters. On the right side here we have the power supply connections. So this is where the 9 volt battery will be connected. And just below is the SMA connector, so for the radio frequency output. On the left side, I left some pads to create the pins with which I will be connecting to the circuit that I want to measure. And well, the core of the circuit is this transistor. And now there's not a lot of special rules applied, other than the input signal line has lots of cutouts around it to keep its capacity as small as possible. So to influence the measurement as little as possible, I have the two capacitors in series, then I have the two resistors quite far away from any ground, and even this input pin, so the first gate of the transistor, has a cutout around it on both layers. And then, well, there's a ground plane beneath the entire circuit on the second layer, but not around this pin. So time to build it and see if it works. So this is the final thing with all of the components assembled, and I also prepared a 9 volt battery connection. So other things to mention is this small plastic case that I also prepared, so just to keep it safe so it doesn't get damaged while being used. So let's see how the probe actually works. And for that I prepared the setup right here. So I have my signal generator and I'll be using it to output a sine wave. And on the one side this is connected to the first channel of the oscilloscope, so the yellow channel, and the signal generator output is also connected to the probe, which is then connected to the second channel of the oscilloscope, where I also have a 50 ohm termination resistor. So now if we connect the battery to the probe, so I'm using a generic 9 volt battery, nothing happens. But now if I turn on the signal generator, we can see in yellow the signal coming from the generator and in blue the signal coming from the probe. So right now the input signal is at 1 volt per division and the one from the probe is at 100 millivolts per division. So the probe is not really attenuating by a factor of 10, but almost. Now this could be fine-tuned by adjusting one of the capacitors. Either the series capacitor, so the one on the probe tip, or the parallel capacitor on the transistor gate. So based on the capacitance ratio between these two capacitors, you will get a certain attenuation on your AC signal. So now, let's see what is the maximum voltage that the probe can accept. So right now the input signal is at 3 volts peak to peak, so plus minus 1.5 volts. But if we increase this, so let's just reduce a bit the amplitudes. So right now we're at 5 volts peak to peak, 6, 7, 8, 9, 10. So at some point, you might notice that the output signal, so the blue sine wave, isn't very sine wavy. So the lower half is starting to saturate, and well, we can see this a bit more better if we further increase the input signal. So the larger the amplitude of the input signal, we will start to see the lower end of our probe response clipping. Now this of course can be improved by adjusting the voltage divider from which the reference voltage is set. So right now I have a 3.3 kilo ohm and a 4.7 kilo ohm resistor, but we could maybe put in a potentiometer or something to fine-tune this value so that the signal is perfectly centered. But anyway, regardless, we should be able to measure quite easily and quite well a plus minus 5 volt signal. So for that at least the probe should be good enough as it is. So next, let's check out the bandwidth of the probe, and for that I prepared the spectrum analyzer, and I'll be using the tracking generator function. So I already performed the calibration, so to normalize the output in reference to the input. And if we connect our probe, so since the probe doesn't have a proper 50 ohm input, it's a high impedance input probe, I have the 50 ohms here on a termination, and I got this T-junction thing. So this is not an ideal high-speed setup, but it will do for today. So now if I connect the probe, so apply the battery voltage to it, we can see that we have quite a flat response throughout the spectrum. So we're starting at 9 kHz, but the slow frequency response is a measurement error coming from the bandwidth setting. And above 300 MHz we have a spike, and then the response starts to die down. So this peak here is mainly caused by the setup, and in theory the probe should have 5, 6, 700 MHz of bandwidth. And that is pretty impressive for such a basic design. Now regarding the low frequency response, this is mainly impacted by our input capacitor and the pull down resistor. So in my current design I have 0.5 picofarads and 4.4 mega ohms, but you can of course increase the resistor and well increase the capacitor if you really want low frequency bandwidth. But for today's experiments I will leave the probe as it is. Now since the high frequency gain spike looked familiar, I went back to the simulations to see exactly what's going on, since the AC simulation that we previously performed was already predicting something similar happening. Now it turns out that the transistor has some quite significant input capacitances, so gate source capacitance of 2.1 picofarads from the first gate, and also a 1.2 picofarad capacitance from the second gate, and above a gigahertz these capacitors become quite significant. So I created a copy of the initial simulation where the transistor was only replaced with these two capacitors, so the gate source capacitors. So there's absolutely no amplification going on. And if we look at the output, we can see that above a gigahertz, the two circuits give an almost identical response. So as frequency increases, the signal will just pass through the transistor without being amplified. And we can also see this with our first simulation. So if we check out the current that's coming into the probe and the current that's going out into the load, we can see that above a gigahertz, more current is being consumed from the signal source than is provided. So the probe is definitely not amplifying above a gigahertz. Now in the practical design, of course, this capacitor can have different values than the typical value of the datasheet, and other than this capacitor, some other parasitics, both from the layout and from the components used, will have an impact on this gain peak. So the gain peak can be shifted to lower frequencies if there's more capacitance present. So finally, let's try to measure an actual crystal oscillator. So what I got here is a board, which I've used in the previous videos on crystal oscillators. So it has a PIC microcontroller, with an 8 MHz external quartz crystal and, well, the necessary capacitors and resistors, and the oscillator is set into HS mode. So now the probe is powered, connected to the first channel of the oscilloscope with a 50 ohm termination, and if we connect it into the circuit, so onto the XO pin of the oscillator, we can see a signal appearing. So it's running at 8 MHz, and it doesn't look perfectly like a sine wave, but this is the sort of signal we can expect when looking into the oscillator. Now, the other thing that we can do now is see just how much of an impact our probe has on our circuit. And for that I prepared my signal generator, which also works as a counter. So my board is also outputting a signal that is proportional to its oscillator signal and 16 times smaller. So for an oscillator clock of 8 MHz, we should be getting 500 kHz. So right now, the counter is on. We can see that we have 9.3 ppm more than we should be having. So this is the precision of the oscillator by itself. But if we also connect the probe to the circuit, so we can see that the precision goes down to about 8.5. So with the probe 8.5, without the probe 9.3. So the probe actually does have very low capacity, and we can see that it has a minimal influence on our oscillator. So 1 ppm of deviation from its reference value is a very good result. Now, of course, the large 47 picofarad load capacitors are also helping, but nevertheless, whatever probe you're using should have a smallest possible impact on your oscillator. And now, knowing that the probe works and that we have a good measurement without too much of an impact on the circuit, we can finally perform our startup measurement. Now, before performing the measurement, we need to do some settings with the oscilloscope. So with a time base of 40 nanoseconds, we see our 8 MHz clock signal, so everything is fine. But to perform the startup measurement, we need to work at a completely different time base. So something in the order of milliseconds. And now what we see here is that we again see a sine wave. But this time it's at like 58 Hz. And that's not a real measurement. We still have our 8 MHz signal here. So this is a measurement error coming from the oscilloscope based on the number of points and the timing at which they are being taken. So to make a correct measurement at this time scale of a completely different frequency, we need to set the oscilloscope into peak mode. So now it just gives us a complete blur, but this blur is far more accurate than the 58 Hz sine wave. So now I'll turn off the oscillator, set the oscilloscope into single mode, so to trigger on the rising edge of the input signal. And when we turn on our oscillator, so let's just move things around a bit, we see our startup pulse, so this is where the power is supplied, and then we see the oscillation slowly building up. So let's just make another oscilloscope capture, another startup, and now we can more clearly see what's going on. So we have our startup event, and then we see the oscillation building up. So what we're interested in is the timing between this supply event and when our oscillation gets to about 95%. So you can use automated measurements for this, or you can eyeball it and say, well, it's around here. So after about this point, the oscillation is flat, there's no more amplitude increase, and we can see that we have 34.5 milliseconds in between the two events. So this is quite a slow startup for an 8 MHz oscillator. But this is the value that we're getting with the current configuration. Now, startup time can be influenced by the amplifier gain. Larger gain will yield shorter startup time. And in this regard, some circuits will use different gain settings for startup and for steady state. So they will use large gain at startup, so start oscillation really quickly, and then switch to a lower gain setting once oscillation only needs to be maintained. Another thing worth mentioning is that startup can be different when a circuit is first powered on and when the circuit is just waking up from a low power or sleep mode, the latter being more detrimental. Since there is already some voltage in the circuit, the initial startup spike will be much smaller, so the oscillation will start up a bit more slowly. So in case your circuit can experience both cases, power on and wake up, both of these need to be tested. In the end, the important thing to remember about this measurement is that since it's performed by directly probing the oscillator circuit, a very high impedance, both high resistance and low capacitance probe is needed to perform the measurement accurately. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos. And see you next time. Bye bye.